Okay, welcome everyone to this weekly meeting on quantum information and foundations. And today's talk is going to be a continuation from the last meeting. Our speaker is Souradeep Sasmal, and he was talking about randomness and how to detect or certify randomness. And okay, so Shoradeep, you can start. And also, before we start, I will let you know that if you have any questions, like any other meeting, you can unmute yourself and ask your question. And also at the end, hopefully, we'll have some time for discussion. Okay, Shoradeep, please start.
Okay, yeah. Thanks, Sundar. So last week, I was talking about randomness certification and quantification, and I talked about that randomness is quantified in terms of mean entropy. So today I will just quickly recapitulate all the things, and then um I will move on. So, so basically, why randomness is important? I must stress on this recent research article. It is very nice article by Professor Valerio Capraro from Milan. They actually studied the gender biasness in StatGPT. For example, actually they asked this question: is it okay to abuse a woman to prevent a nuclear apocalypse? And ChatGPT says strongly disagree. But if they ask about that, if it is okay to abuse a man to prevent a nuclear apocalypse, ChatGPT says somewhat agree. So basically, what they think that the learning process of ChatGPT remain become little bit biased, intentionally or unintentionally. So they urge that whoever working with this kind of machine learning language, the input learning should be unbiased. So that means you need a proper random number which is not apparent or which should not fail in NIST test. That kind of things to learn your machine learning language. Otherwise, it will create many biases. Anyway, so I talked about the existing random number generators. That means the pseudo random number generator based on mathematics, the true random number generator based on classical phenomena, or the quantum random number generators. They have some problems because this privacy can be a problematic that I talked about, and also if those keyword, if those RNG deviates from the intended design, then we don't know what is how basically how we can certify those things. So these are the reasons we need to go to the device independent random number generator, where the Bell inequality violation plays the crucial role. So in Bell inequality violation, actually, when a statistics violates Bell inequality, we actually get some non-uniform random sequence from the output of a Bell experiment. But to make it usable, we need to make that non-uniform random sequence to a uniform random sequence. And this uniform random sequence must be shorter in length than the non-uniform random sequence, because we will cut down some non-uniformness from the initial sequence. So basically, how much uniform sequence one can extract maximally from a non-uniform random sequence, that people have proved that it has a bound which is connected with the mean entropy. And this connection actually people have done in the classical random theory, and also uh, mm, this paper by Koenig and Renner in 2009, they have established that connection, that the guessing probability of this non-uniform random sequence is basically bounded by the relative entropy of A given B. So, so basically, in summary, if you have a probability distribution, then the randomness amount of
Shoradeep,
randomness present. Yes.
yes, I have a small question. Like, I mean, maybe it is not related to this thing, but uh, can you just tell us that why is it important to get uniform random sequences? Because for some practical applications, you might need a distribution that is like Gaussian or something like that, or normal distribution or something. So those are kind of useful in many cases. So why we want to extract the uniform random sequence from it?
I mean,
Like
let's say
uniform
for
random sequence, you mean the like all of them having equal probability, right?
yes, yes. For example, let's say you have a biased coin of probability P and 1 minus P, right? Now
Mhm.
you want to input a random sequence of head and tail into your device. Now it
Mhm.
would be better if you input the head tail probability is half, right? In the sense
Mhm.
because uh, how can I say? Then it will not be more biased towards head or more biased towards tail, right? The
True,
device.
true, true, true. Yes, yes, yes. That is true.
In that
Yes.
sense. So now one can
Mhm.
ask that if I have a biased coin, then how can I create a uniform probability distribution? So basically what you
Mhm.
have to do, you have to take two biased coin with same biasness
True, true,
parameter,
true, true.
and then you can see the probability of head tail and tail head are equal. So then
Yes,
your
yes.
string becomes a little bit shorter and you can use it.
Yes, yes. No, no, no. I'm just saying, like, this is just a curiosity that in those random trials or some things, so there people
Mhm.
usually use the uniform random sequence or some other non-uniform random
Maybe to
sequences are
remove
also
the
there.
biasness, maybe to remove the biasness towards any of event.
Okay, okay, okay.
Shomda, uh,
Mm.
I can comment on that in different context. In the sense that when you have this random trial, for example, drugs. No,
Yes.
you want in that like drug trial, you have the in the population you randomly select samples and give either the placebo or the drug.
Mhm. Yes.
So so that is because to check that if the placebo is like to see whether the drugs is actually effective as a medicine,
Yes.
and it should have some observational effect on the disease even if you choose the parties randomly, like so
Right. Mhm.
that's why the uniform
Yes,
random distribution comes in that particular context
yes.
of the drug trial.
And one thing I must add, even if you are using an biased sequence as your input, people have found out some statistical analysis to remove the bias and all those things. So, but the thing is, if your input distribution is uniform, maybe the statistical analysis become more simpler.
Okay, 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 okay. Okay. Mhm. Okay. Please continue.
So, so
Sorry,
basically, if you, huh? Any other question?
Shoradeep, just I'd like to add one
Hmm.
point. Maybe something like this is kind of a process of distillation, like where you are actually starting from some non-uniform random sequence of n. Over there, you have that pi running from 1 to n, and now you are having a uniform random sequence where each of the probabilities are 1 by m. So we know that uniform where this m is less than n, and we also know that for any uniform distribution, the entropy is the highest. That means the bias will be the lowest over there in that particular case. So
Hmm.
that non-uniformity, which was actually there in the largest sequence, is no longer there in the case of the smaller uniform random sequence. So it is more random in that one, and so some bias has been removed. I think one
Yeah.
can be in that border.
Yes, actually, I can comment on that. In this paper, they have actually proved that the minimum entropy of a state is basically the singlet fraction. Minimum
Mm.
entropy of a bipartite state, it is actually the singlet fraction of that bipartite state. I have not understood the proof correctly or the statement itself, but I can understand that it is related to this purification problem or distillation problem, something like that. This
Yes, yes.
specific quantity, this minimum entropy, because
Ha, ha,
minimum
ha.
entropy captures only the maximum probability in that event. And we are
Mhm.
trying to create a uniform random sequence of that probability, something like that.
Yes, yes. So actually you have a bias in many sequences, but then you are getting a fewer number of sequences which does not have any bias at all.
Hmm. Exactly, exactly.
Yes, yes. Okay, thank you.
So basically, so if you have a probability distribution, the randomness present in that distribution is quantified as minus log 2 p max. And what we understood from this different literature that it is the correct way of doing it in the sense in the security aspect also or in other aspects also. Uh, so basically, the randomness discussion is divided into two parts. The certification process, which is nothing to do with quantification, and certification process is the theory. It should be theory independent. That's then it will be a proper random against any kind of adversarial attack or something, and which can be done with the violation of Bell inequality. And the second aspect is the quantification, how much randomness present in a sequence, and that is theory dependent, because whatever theory you are using to produce that sequence, that some constant on that theory will give you the amount of quantification. For example, in quantum theory or in signaling theory, you can calculate these things. So basically, in the Bell scenario, we define a Bell functional which acts on the set of probability distribution, which is called behavior. And if Alice and Bob observe this PAB XY in their lab, then the question is how I can quantify the amount of randomness from this distribution. Now the thing, we assume that Eve is actually producing this distribution in Alice and Bob's lab, and this S is called the strategy, and it can have different strategy to produce this observed behavior. Maybe Eve is creating a tripartite joint probability distribution PABE, and from there Eve is only giving PAB XY to Alice and Bob. So there may be different strategies. So in general, we can write that there are some probability distribution which Eve can't access, which we call the extremal probability distribution. I will come into that. So in general, there can be different strategy, and in that way, you can produce this joint probability distribution. And for the certification process, the Bell value of this behavior should be greater than the local bound. So basically, the Eve's guessing probability is the maximum value of PAB XY S, and you can see the first line, the guessing probability is dependent on the strategy. Now, since Eve controls the strategy, we have to optimize over all strategy also to get the guessing probability corresponding to the outcome X and Y. In the last line, in the left-hand side, it should be G of XY. I forgot to put it there. So that's the same thing. I wrote it in a more concrete. Now it is corrected that the guessing probability when Alice measures X and Y measure and Bob measures Y, then the Eve's guessing probability to predict the outcome A and B is basically this. Again, for each strategy, it has some guessing probability, each strategy SI. So since Eve is producing this behavior P vector by convex mixing of different strategy, so the Eve's guessing probability will also follow this convex mixture, and the final randomness will be calculated from here by solving this optimization problem. And you can see this is basically a linear program. So let's try to first understand how we can quantify the randomness in a no signaling theory. So the no signaling, I am only considering 2-2-2 scenario for simplicity, but all the arguments can be generalized in an arbitrary NMD scenario, which will be more complex. So in the 2-2-2 scenario, we know there are 24 extremal distributions which characterize the whole no signaling theory, and it creates a polytope. And out of 24, 16 are local distribution and 1 are PR box distribution, and one of the PR box distribution looks like this. And if you permutation combination this position of up, you will get 8 different kind of PR box distribution. The PR box distribution has CSSH value 4, and the local distribution has CSSH value lies between actually -2 to 2, but let's for simplicity, I will always take CSSH value 2. So these are local distribution. You can see when Alice and Bob measure 0, 0, only one event can occur and other event should be 0. So it's kind of, I'm telling it local distribution, but it's actually in operational level, we should say that this distribution is called predictable distribution. But anyway, this is just a terminology people use. And since the no signaling theory is a polytope, we can always characterize the facets of that polytope. And after solving the facets, we will find out that there are 4 CSSH expression and some other probability positivity constant. So with that facet, one can construct this polytope, and I took an example that this line is one of the facet which is CSSH equal to 2. So let's say I have a distribution which comes from this predictable no signaling set. Also, we can say local deterministic set. And this distribution can always be reproduced by taking convex mixture of all the local distribution, right? And since each local distribution means the guessing probability is 1, so randomness will be 0 for any distribution which is inside this local distribution box. And those distribution CSSH value is less than 2, obviously. But let's take a distribution which is outside the predictable no signaling box, and which is the red distribution I am talking about. And this distribution can be decomposed into, in general, can be written by convex mixture of all the local and the PR box distribution. Mind it, sum over Qi plus Q dash K equal to 1. It's not. So these are the same convex mixture. And since I know the guessing probability of this distribution would be, then for local distribution it is 1. For PR box distribution, it is half, because we already saw that in the PR box distribution, the distribution is half 0 0 half. So the maximum probability is half. So in that way, I can actually calculate the guessing probability in this manner, where 1 minus half into sum over Q dash K, and the randomness will be this. Now what is the CSSH value of this distribution? The CSSH value of this distribution will be, again, one can find as a convex mixture of this CSSH value of local distribution and CSSH value of PR box. So I just took CSSH value as 2 and PR box distribution as fixed CSSH value 4. So then one can actually express the amount of randomness as a function of CSSH violation in a no signaling theory. So you can see, if I plot this distribution, I will get a monotonic increasing term if I plot in y-axis randomness and the x-axis CSSH violation. And if CSSH value become 4, you can see that randomness will be 1 bit, because if it is 4, then it is half, then R will be 1. And if CSSH value is 2, then R will become 0.
Suradipta, are you showing any graph?
I don't have any plot. I can draw the plot.
I was thinking that, are you changing the slide or not? Okay, no problem. You're not changing the slide. Okay, it's okay.
I actually done something wrong. Wait. Where is the writing option? Wait. Okay, let me share it again. One second. It's visible in the screen, right?
Yes, yes.
Yeah. So for this, the graph will somewhat look like this. So if I plot randomness in y-axis and CSSH value in x-axis, and let's say it start from 2 to 4, then the graph will look like somewhat this, and this is 1 bit. So just one can directly, it's a simple plot one can do.
So actually here is, I have one question. So can you show us the function of R? I mean, how it is dependent? I mean, can you
Yes,
go
yes, this
before?
is the
No,
function
can you
is,
go to the earlier slide where you're doing maximizations?
yes, yeah, this slide, the R is calculated here. Right? You can see the distribution, I have written it in a more
No.
general form, right?
Yeah, it's okay. But let me ask you this way. So first of all, initially your R was, I think, something minus log 2 of some P max
Yes,
of
you can see
ABXY.
that, yes, just let me explain that.
I'm just, let me just ask my
What?
questions.
Yeah.
Yeah. So you see, I have some probability distributions PAB given XY, and then R is equal to minus log 2 P max PAB given XY. It was like that. So it is not a linear functional, right? It's look like not a linear functional. So it is not a linear
There
inequality
is
probability.
minus log 2, so it is not linear. I also
Now
have
what?
not drawn linear, right?
But you see, no, linear means what I'm asking, you see, you are getting optimum value of R in the extreme point of your polytope, which is actually true for some convex or concave functions. Okay.
Yes.
But your function, when I'm just, I mean, somehow this maximizations, minimizations, whatever you have done in the process, I mean, it could happen that, okay, in the extreme point, it is not giving you optimal. Rather, in a non-extreme point, it is giving optimal. It might happen
Okay.
that if I take a convex combination of two PR, then R is maximum.
Okay. Okay. Let me answer your question. So this P vector is written in a more general form. Do you agree? You cannot write it more general, and you have to remember Qi plus Q dash K is equal to 1. Okay.
Yes.
So any behavior inside the no signaling polytope can be written in this form, right? Now, if I want to calculate the guessing probability from this behavior, then it will be like same thing, the guessing probability of the local distribution plus guessing probability for PR box distributions, right? Now, what is the guessing probability of local distribution? That is 1. So I can write G of P vector is equal to sum over Qi plus sum over Q dash K. And what is the guessing probability of all the PR box distribution? This is half, right? Now I can replace this sum over Qi is basically 1 minus sum over Qk, right? And if I do the and then if I simplify it, then your guessing probability will become 1 minus half sum over Q dash K, right? Now this is the maximum probability, basically, corresponding to this distribution. I mean, you can guess with maximum of this. So your randomness will be minus log 2 this, because randomness is ultimately minus log 2g. Here you see, you don't see the optimization problem because the theory is polytope, and I can characterize any distribution in terms of the extremal distribution, right? So that's
Yes.
why the optimization is not required. I mean, here I have done the optimization. Guessing probability of local distribution is 1. That is your maximum value. I already took it. So that's why this maximization problem is gone, and we can solve the problem totally in the no signaling theory.
Souradeep, sorry, me, do you want to ask anything more? Because I wanted to ask.
Proceed. Yeah.
Yeah. So this guessing probability, this is for, I mean, after the optimization, it is for some fixed setting, right? X and Y.
Yes. It should be.
But when you write the convex combination, how are you sure that it is going to be the same XY for the local and the PR
Okay.
box?
Yes, good question. I should have said that for the local distribution for any XY, all the XYs are equal actually, right?
Yes, yes.
Is equal to 1. And same for PR box also. If it is local distribution this, and if it is PR box half. So
So in
basically
general,
for
generally
all
for the convex
XY,
combination, Yeah.
Yes.
In general, for
Otherwise,
the convex combination, it should not be true, but it is for the local because you already know, guess completely the local one. So it
right.
just comes to the PR box. Okay.
Right. Let's say you have a distribution. Let's just assume you have an extremal distribution like that. That it is, let's say, sorry, let's say this is 1. This is, let's say, some 3 by 4 and 1, 1. Let's say you have this kind of distribution. Then you can see that for 0, 0 settings, the guessing probability is 1. For 0, 1 settings, the guessing probability is 3 by 4. So then I should have written XY in the left hand side. And then then there will be a 4 different amount of randomness corresponding to different combination of X and Y. And from there, we can again take R mean or R max that I will talk about actually. But for this case, when the distribution is local and PR box, you can see for all XY, those values are same. That's why it doesn't
Yeah.
matter.
Yes. Yes. And this also answers this question because
Yeah,
it finally reduces to the randomness of the extreme points.
right. It finally,
But Sumda, suppose you have a line, you have a probability, yeah? You have a coin, okay, P1, P2, okay.
Mhm.
So one end it is 1, 0, and another end it is 0, 1. But you see the randomness is maximum in the in-between point. It is not in the extreme point, okay. Same things for any simplex. Any simplex
talking
probability,
about
same
one
things
thing.
happens.
But
Just now,
here, I guess but here I guess the mixing, we are not looking at the randomness of the mixing like the classical randomness, shared
Yes,
randomness.
classical randomness I don't want, because otherwise the
Mhm.
randomness present in p vector may be more than what I am claiming, because here I am quantifying randomness in terms of adversarial perspective, what adversary can do with this distribution, right? So maybe the randomness present in this particular distribution is more, but that randomness is not a safe randomness, because adversary can always prepare this distribution by convex mixing of local and PR box. And for local distribution, adversary will have zero randomness. And by using this convex mixture, adversary may guess more, because you know this inequality, right? That P max of the distribution will be always less than equal to sum over Q of P max of extremal distribution, right? It comes from that inequality that our Renyi entropy is always greater than equal to alpha into Renyi entropy some x1 distribution plus 1 minus alpha into Renyi entropy of x2. I mean, let's say you have x1, you have one distribution y, which you can create like this, alpha I xi, then it can be proved that Renyi entropy of hy should always be greater than equal to
yeah, I got that point. I got that point. It is from the some adversarial point of view, how much local is actually mixing. He can adversarial from an adversarial point of view. Those local things, from the local things, I cannot extract randomness. Okay,
exactly,
I got. It is only coming from the PR because their adversarial rule is very nominal. In fact, 0.
exactly.
That's why I will take only from the PR contributions, and that's why PR contributions will give the maximum, because
Yeah,
local points are
that
controlled by the adversarial. Okay, I got it.
exactly,
Thank you.
exactly. If I extrapolate your statement just a bit longer, that means the H mean of this distribution is basically your PR fraction, right? Now I understand this statement by coming. That why a mean entropy of a quantum bipartite quantum state is its singlet fraction. Because the randomness present in this distribution, the origin is actually in PR. And how much you can distill PR from this distribution, that is your amount of randomness. That is the minimum entropy of this distribution.
Yes.
Now let's make the situation more more complex, more groomer, because in quantum mechanics, because the quantum theory is not polytope, but it's a convex set. And don't ask me why it is not looking smooth convex, because I have drawn it in my hand, so it should be smooth. So anyway, so let's say now the distribution is now that this p vector has a quantum realization. So that p vector can come from anywhere. And we know for sure that if we are taking CSSH as a Bell inequality of our certification process, then if CSSH become optimal, that is true in quantum mechanics, then this point is optimal, and there are a lot of literature. It's called Cyrelson point. And since the Cyrelson point is unique, if we assume that our adversary is constrained by quantum theory, then adversary can't access the pink region, the PR box region.
Hello. So, Souradeep, I just want to make one point clear. So, suppose somehow you got to know the PAB XY, which point it is. Okay.
Yes.
Somehow you got to know. Okay, not from the CHSH value. Rather, you know the microscopic description that okay, this is the PAB given XY.
Okay, let me write. Let me write. Let's say I know this, right? What you are saying.
PAB given XY. Yes, this probability
that is my
you got
observed behavior. Yes,
that is your observed behavior. Now, what I'm asking, since this is the simplex, okay, this is, if it is non-local, then it is going to be a simplex. Only unique decompositions of PR and local. So you can find out what PR contribution it is, right? And then it would be very easy problem.
Yes, absolutely.
Okay. Thank you.
But if it is quantum, then it will be very tricky, right? Because that can come from many set of state and many set of measurement strategy, right? There is no unique way of creating this. If it is not quantum extreme. For example, if it is a Cyrelson point, then I can say, okay, this can only come from a specific state and measurement up to local isometry. And even if you apply those unitary, this T vector will not change. So here the amount of randomness is 1.23 bits against the quantum adversary. I mean, if you allow the adversary to be a no signaling adversary, then this amount should be less, right? Because then I will treat this T point, I will calculate the randomness from T point from this picture, if my adversary can access the whole no signaling set. And since we agree that quantum theory is the physical theory and all other things are non-physical, if we restrict ourselves in that argument, then adversary also restricted by quantum theory, and then this becomes 1.23 bits. So now it actually presents a very intriguing fact that since CSSH is a very good measure of non-locality in the 2-to-2 scenario, then the quantum theory has more randomness than the no signaling theory. Although the no signaling theory allows more non-locality, So maybe one can ask that whether quantum theory is the most unique theory which gives you the most randomness or not, this kind of question, but I'll come into that later. So now let's say the situation is a little bit complex when the quantum distribution is not the P vector, any distribution inside the quantum set. Then how we can calculate the randomness? Again, we will assume that we will consider that adversary is producing this particular behavior in something like convex mixture of some quantum extremal and some local distribution. Here, this P ext belongs to the quantum extremal set. Okay, but you can see
just one confusion. So whether in the log you have written 1 plus minus 1 by 2, why minus? It should be only plus,
no.
right?
It should be only. It should be only plus. I actually copy pasted from the expression. Okay. So now let's say just I'm taking an example. Let's say how adversary can doing this. That adversary is accessing another one extremal quantum correlation which has more CSSH value than the observed one, and this local box. And by taking the convex mixture of L and P ext, adversary is producing this green distribution. And then the guessing probability of this green distribution should be like this, because the local distribution, the guessing probability is 1, and the pxt, there the guessing probability, here I put the guessing probability of pxt. And the CSSH value of this green distribution is 2 plus epsilon, and the CSSH value of this purple distribution is 2 plus epsilon 1. So one can actually get this. If I take a very simple example that only Q1 and 1 minus Q1 is there, then one can write the amount of randomness present in this green distribution is like that. And again, if you calculate this directly from this P vector, then it will be more. And if you take this convex mixture, it will be less. And one can actually solve this problem in general. That now, Somda, you can see I put this xy in the R, because randomness corresponding to the measurement settings x and y, it is in left hand side. And basically this whole problem boils down to solving this optimization problem, that this is trace of row MA tensor MB is the Alice and Bob's joint probability PAB, and to get the amount of randomness, we have to optimize over all possible row, all possible measurement strategy, which gives me this P vector such that CSSH value of P vector is 2 plus epsilon 1, and epsilon 1 should be greater than 0. Now, in that way, if for a given CSSH value, let's say this is 2 plus epsilon 1. Yes.
Can I interrupt? So you see, first of all, I'm a little bit confused, but okay, I need to make it clear once. So the approach was you have a PAV given xy, you try to find out the combination of qi and q prime extremal, and then find out the how much PR is included. From there, you try to see the
PR. Here PR I cannot include, right? Because
no, I'm saying one of the things is that two way one can tackle this problem. One is that okay, it is a non-local correlation, so then obviously some PR contribution is there. Theoretically, PR contributions I can assume. Okay.
Right, Mir, before you ask me the question, just let me be clear on one thing. I have assumed that adversary is constrained by the quantum theory, so we can't access PR.
Agreed. Yeah, I understand.
If you are telling that adversary can access PR, then this is the way of calculating the randomness.
Exactly. And then it would be very simple, right?
Right, it would be very simple. Yeah.
Very simple. So I'm saying, so that's why I just need to clear myself. So when you are showing that, okay, 2√2 correlation is actually exceeding the randomness of PR, it's giving is 1.23. So actually, in that protocol, your adversary believing the structure of quantum theory in that way, right?
Yes. Adversary can't access PR. If adversary access PR, then the randomness present in this T should be less than 1.2.
Less than
because
1.2.
We have
not only 1.23, it should be less than 1.
Exactly. Because we already saw this curve, right? It is monotonically increasing, and the PR box has the maximum one. Right?
So this monotonically increasing function is believing on the PR theory. It is. Yeah. Okay.
Against the PR, against the no signaling adversary, and this 1.23 against the quantum adversary.
Yes. I'm saying that portion could be confusing me. Okay. Thank you. Okay.
So basically, we need to solve this problem to obtain amount of randomness. I mean, there may be a two question. Question number one: how much randomness present in this green dot? And another question is, if I see this Bell violation in my lab, 2 plus epsilon 1 CSSH violation, then from the statistics, how much randomness I can trust. So you can see that can be completely two different answers. That how much randomness present in this green dot, that means I know my distribution. Still, how much randomness I can quantify from there. So that is a different issue. And another thing is, one can, since usually the Bell violation is the operational quantity we see in lab, we don't see our PAB XY. So that's why in my lab, if I observe 2 plus epsilon 1 amount of CSSH violation, then whatever statistics I have, how much randomness present in there. And maybe if I only see this amount of Bell violation, maybe that Bell violation comes from any point on this line, right? And to evaluate that randomness, I need to solve this optimization problem. Now, from here, if we look into it, that it is dependent on still X and Y, and depending on that, I can define two quantity, R mean and R max. That means if I take the minimum value over all the possible combination of measurement settings, I will get R mean, and if I take the maximum amount, then it will be R max. Again, for serial standpoint, R mean and R max are equal because the distribution is symmetric in such a way that all combination will give you the same amount of randomness. But one can think that if I am talking about device independent randomness generation, okay, before I go into that, there is a result regarding the R mean, that if one solve this optimization problem and calculate and taking the minimization over all settings, they will get R mean for each observed Bell violation, and then you will get a curve like this. If I plot R mean versus CSSH, it will be like this. Again, it will become monotonically increasing, and this point is 1.23 bit, and this point is 2√2. To compare with the no signaling theory, the curve was like that. This is 1 bit. So quantum theory always certify more randomness than the in general no signaling theory. Yes,
it is not 1 bit. It is less than 1 bit because
it is 1 bit.
Red card.
Oh, sorry. Card should be like that. This is 4. Yeah, this card. Okay. Yeah. So in the quantum theory, randomness can be more randomness can be certified than the no signaling theory. I think this is a little bit obvious because in the PR box theory, the adversary has more power because the adversary can access more non-local distribution and something like that. So that's why in PR box theory, the amount of randomness is less. This result is by Pironio 2011. They have also done the experiment and generate random numbers from a Bell experiment. It's a Nature paper, randomness certified, Bell's theorem certified random number. And that this one, it was there. So now, but see, when we are talking about device independent randomness and adversary has the full access, then the reliable amount of randomness should be RV. Because
Souradeep,
yeah.
before you move, can you elaborate on the phrase when you said the phrase no signaling adversaries? So
no signaling adversary means that I told you that let's say you have a distribution of this serial cell point. Okay. Now, if adversary can access PR box, then the amount of
explain to me in terms of operationally, because no signaling is an operational thing, right? So you have Alice's input doesn't depend.
Okay. So basically, Alice and Bob, they observe this. 1 second. They observe this behavior, right? Now, what Eve is actually doing, some run of the experiment, Eve is providing them PR box, and some run of the experiment, Eve is providing them local distribution. So those runs where Eve provides local distribution, there Eve completely know what should be the outcome, right? And for PR box, he know, he doesn't know, he will wildly guess some output. Now the question is the guessing probability of this serial cell behavior, whether it will be same if Eve takes this strategy when Eve is giving PR box in some run and local box with some other runs. So actually, in this way, if someone calculates the guessing probability by taking into this strategy, then people will find out here the guessing probability will be
Yeah, that
more.
is what you showed. Okay.
Yeah, yeah.
Yeah, okay. So here the no signaling adversaries mean that Alice and Bob are no signaling, satisfies no signaling between them, and
No signaling always satisfied. No signaling adversary means adversary can access the PR box physically.
Okay, the extreme points of the no signaling.
Exactly.
Okay, okay.
So let's say people have found out there exists a physical correlation. I mean, in lab, if someone observe a correlation which has CSSH value greater than 2 root 2, then you can be sure that, okay, maybe PR box theory is a physical theory, but still we don't know. So I'm just assuming hypothetically that if our world is a only no signaling theory world, that means there is no constraint, only no signaling is there.
Yeah, I understand.
So yeah, Armin should be the most important quantity because it also doesn't depend on the choice of combination of measurement settings Alice and Bob are employing. Then why suddenly these Rmax terms become important? Why we should take Rmax also a secure quantifier? Yes, Armin is the most secure, but Rmax quantity becomes important when we actually operationally generate randomness. Because to generate randomness, we have basically two processes. One is called spot checking, and another is called randomness generation. So that means, let's say for n equal to 1, and there is again a random number generator is there, and each run of the experiment, that random number generator will tell me in this run whether it is a spot checking round or whether it is a generation round. If it is a spot checking round, then Alice and Bob will choose A1, A2, or B1, B2 randomly, perform the experiment, and record the data. So let's say this is a spot checking round. Spot checking round. Let's say n equal to k is a generation round. So when the generation round will appear, then they can choose a perfect measurement settings, which gives them the best chance to produce more randomness. So that's why this Rmax quantity becomes important. Because you see, in the spot checking round, why it is called spot checking? Because after so many rounds, the spot checking rounds data, they will share each other and they will check whether it is violating CSHH inequality or not. So that's why it is called spot checking. It is called checking. Why it is spot? Because let's say after 100 runs, they will check CSSH is violating or not. After 300 runs, they will check CSSH is violating or not. And that's why it's called spot. Because at that spot, they will check. And these data where they have used to check whether CSSH is violating or not, those data are gone. Those data are not useful for randomness. Why? Because privacy is compromised. When they have shared this data to each other, then adversary knows the output. So it's like a adversary using a memory to create a random sequence. So only the data from the generation round will directly go to the required sector where the randomness is required. So that's why when the generation round will be tweaked, Alice and Bob will make sure they will measure in that particular direction where they have a maximum randomness. So that's why Rmax becomes actually the operational meaningful quantity. And also Rmax is also secure like Armin because it is the optimized over all possible state measurement settings and all that. Let me give you an example, then it will be more easier to understand. Let's say they know that they got this kind of they are expecting this kind of distribution from their experiment, that let's say some p vector is this. For 0, 0 settings, they are getting 1/4 probability, and for 0, 1, 1, 0, 1, 1, they will get some other probability. Now, when the generation round will come, they will always measure A0, B0 to produce, and whatever the sequence will be produced from these settings, which will be a uniform random distribution. So, but you can see that if it is, let's say 3 by 4, 3 by, I am just writing it randomly. Okay, so then basically the Rmin should be minus log 2 3 by 4, minus log 2 3 by 4. But Rmax is minus log 2 1 by 4, because R00 is minus log 2 1 by 4, R01, R10, and R11 is minus log 2 3 by 4. And also I must emphasize this fact that what Shonda actually asked the previous week, that actually doing the Bell experiment, we need random numbers. So let's say at first, let's say to select whether my round is generation round or my round is spot checking round, I need smaller amount of randomness for some total n number of runs, and I will take that sequence in such a way so that the generation round will be more and spot checking round will be less. And we also need some randomness to select which setting I should use. And that, if I am using CHSH inequality, this should be 1 bit random. For Alice 1 bit, for Bob 1 bit. So it should be total 2 bit random for some number of round where n is much less than capital N, because n is the spot checking round. That's why we need input random distribution. And this R is giving me to select whether I will do the generation or I will do the spot checking. So this R is actually very small, so that I always do the generation run. And if one calculate the total input randomness from there, and after output, I have generated how many runs? N minus n runs are used for generation of randomness, and let's say I got R output. So now if one can prove that R into n plus R dash into small n is greater less than n capital N minus small n into R output, then actually randomness, one can show that randomness can be expanded. In the left hand side, that random number may not be private, that random number may not be uniform, any kind of thing is there. But in the right hand side, you are getting a private and secret and proper random sequence. And from there, one have to use the proper extractor to get a uniform random distribution, right? And there are 4 or 5 words where they have shown that this is possible in a Bell scenario. So that's why CSSH scenario, I mean Bell scenario, works to create a private random sequence from a non-reliable random sequence. So it's actually randomness expansion. I'm not getting into there. It's a little bit different. Now let's say what are the result in Rmax and how much Rmax I can certify. So in the 2-to-2 scenario, we can see the Rmax can be in principle 2 bit, right? In no signaling theory, for no signaling theory, Rmax, Rmin both are same because they are symmetric and it is 1 bit. The maximum amount one can get from the PR box. But in the quantum theory, whether it is possible to certify 2 bit of randomness. So the first result was that, as in 2012, they have shown that there exists a distribution very close to the local, which has this close to 2 bit of randomness, and they have proved that. Write down the date. So they showed that if one start with this step, psi theta, and there exists some.
You have 5 more minutes, okay?
Okay. And there exists some. So I'm not writing the expression. And they construct a Bell inequality like that: beta A1 plus alpha A1, A1, B2. And there are some local bounds. They have shown that with the state of measurement settings, this inequality can be optimally violated. So that means the behavior coming from this particular theta and measurement choice of Alice and Bob is a self-tested. So that means this behavior is extremal. So that means we can directly calculate the randomness, just taking out the maximum probability for each settings, and from there we can quantify R max. And they have found that the guessing probability is, sorry, the randomness is basically 2 minus some ln2 by alpha, and the CSSH value of this distribution. CSSH value is not for certification, is just for how much non-locality is there to judge by that. It is something like 2 alpha plus 1 by root over 1 plus alpha square. And one can see if it goes tends to 2, then alpha tends to, if you take alpha tends to infinite, this value will go tends to 2, and then 2 bit of randomness will be certified. But still, that result is not so much give us the clarity whether quantum mechanics really certify this 2 bit randomness or not, because it is in the limiting case. Then actually, Ultron and Kolbeck, they have found out that it is possible to generate 2 bit of randomness from the 5 plus, and there exist suitable measurement settings for Alice and Bob, and one tilted Bell inequality like this. A0 B1 plus A1 B0 minus 1 by cos 2 delta A1 B1. When this strategy will violate this tilted Bell inequality optimally, we can say this distribution is extremal, and the CSSH value of this distribution is basically 3 root 3 by 2. And they have shown that by varying the parameter delta, one can actually characterize many extremal quantum distribution which are CSSH value in between 2 to 3 root 3 by 2, where one can get R max is equal to 2B. But what the questions left unanswered, that whether this value is optimal or not. I mean, for Sirelson point, we know the R max is not 2 bit. For Sirelson point, R max and R min are same, so it will be 1.23 bit. And for this point, the CSSH value is 3 root 3 by 2, and the randomness is 2 bit. But in between, whether there exists any distribution or not, that we still don't know. So yeah, so one of the future work maybe kind of try to prove whether this is the optimal limit of CSSH value where one can get 2 bit of randomness, and these results are so in the simplest scenario. So if someone go beyond that scenario, then all the questions is still there to pursue. Because in the high dimensional scenario, we find that it becomes a little bit tricky to find out those kind of distribution where we can get the theoretical maximum of randomness. Because the logic behind this is we have to design a Bell inequality like that. Let's say A1 and A2 are MUB, and B1 and B2 are MUB. So basically, if I add some B3 which is equal to either A1 or A2, then you can see the expectation of A1 B3 will always be 0. So, and also from the definition of MUB, the probability of outcome measuring A1 and B3 will always be 1 by D. So in that way, one can get the intuition that how to characterize those measurement settings to get the maximal random. And maximal random means the uniform distribution. But one need to certify also. So one need to derive a Bell inequality like that, so that the Bell inequality should be optimized for this particular choice of settings. And whatever state you can take, you will always get this is 0. And another kind of future work maybe because it is very good to talk about Bell inequality, device independence, fundamental things and all that. But actually the funding agency always wants some output in 10, 15 years time. So Bell and implementing Bell experiment and make it commercial is a big deal. So what now people are trying to study that, let's say, let's make the situation little bit uh, little bit less complex. Let's say I trust my state. This is, let's say, trustworthy. So it is kind of a semi-device independent. Now, what direction I should measure so that I can generate some certified amount of randomness? This type of question people are asking, or in the opposite way around, if you trust your measurement device, then how you prepare your state? I mean, if you trust your measurement device, that means which direction you should measure so that whatever state if will give you, you can always get an secure and certified randomness. And again, answering those questions are basically related to this fact that if the what I say, if the, let's say, eigenstate of M are like this, then if they form like is equal to 1 by D MUB, then you can always get a secure amount of randomness because it will be unbiased. But the thing is, you have to prove that you have to select a direction in such a way so that whatever state it will give you, you will always get some amount of randomness, because this is the ideal situation. It will not give you the psi if you pre-select your n. And so this question also one can pursue. This is kind of semi-device independent, but still it is more implementable than the Bell scenario. And also one can ask this kind of question. Actually, as in 2015 wrote a paper that whether there exists any other theory than the quantum theory where 2-bit randomness presents or not. Okay, and when I say that any other theory, let's say any other theory is Q1, which is bigger than the quantum set, then the adversary can access Q1. So the certified randomness should be against those adversary which is bounded by this Q1. And by numerical SDP and NPI hierarchy, they shown that this kind of theory may exist. So one can try to answer in a more analytical way. Basically, what I am trying to work on this kind of question, that let's say if I want only this distribution, this I called MR distribution, and this is my theory, MR theory. Now, what should be the CSSH value of this MR theory, maximum CSSH value? And this MR theory is a convex. So then one can construct the vertex. I mean, one can construct the polytope by finding out how many vertex are there, and from there one can actually get the cut where this MR theory cuts the quantum box, that whether if it is 3 root 3 by 2 or it is more than that. So in that approach also one can pursue. Yeah, so I think it's pretty much of that. So randomness is fundamental, keep calm and be random.
Okay, anyone?
So
Anyone
I'll
have
just hello, sorry, sorry for interrupting. I'll just ask a quick question. It's probably stupid. When you show those different kinds of Bell inequalities,
Yeah.
so we would have different local bounds, like if you take predictability and no signaling, then 2, right?
Yes, obviously. That yes, let's say this is one Bell inequality. Let's say this is one Bell inequality. So the local bound will be some beta L.
Yeah, so my question is it may happen, right? The local boxes in the standard Bell scenario, all the local boxes won't be contributing to the beta L in the new scenario. Can it be the case? Like
For
it can
this
just
kind of okay, for this kind of Bell inequality, one can be sure any local distribution should give less than beta L. You can see from the picture. But
Yeah,
there
but
exists some non-local distribution which can also appear to be local with respect to this inequality, because this inequality is not a necessary sufficient condition, because CSSH are the facet, right? So that's why those class are necessary sufficient. But whenever a distribution will violate this, we can be sure that it must be non-local, and it will also violate CSSH always.
okay. Okay.
Oh, another point I forgot to tell that is very interesting actually. Recently, Bankal showed a very nice, they wrote a very nice paper. They were trying to find out, characterize all the Bell functional which will be optimized for the serialization. I mean, they asked the question that whether serialization is unique or not. That is the question. Now, if you ask the question from the dual perspective, whether corresponding the serialization functional, there is a unique Bell functional or not. So they found out actually CSSH is not the unique Bell functional. The dual of that serialization also forms a polytope and has 8 Bell inequality, whose convex mixture is basically a CSSH. So that question also one can ask for different extremal distribution also. Because sometimes some extremal points may be exposed or maybe non-exposed. Exposed mean whether there exists two quantum extremal which are connected by a straight line. That means if there exists a Bell functional hyperplane which will be optimized for two different extremal probability, then we will call those extremal are exposed. And if that happens, I don't know what is the physical meaning, but still one can say kind of thing that if you have a, let's say you got this distribution from E and you are trying to certify the randomness from this hyperplane, then it will be a problem because it can give you another distribution which is on that hyperplane. So we have to use those hyperplane for those extremal, in which case those extremal should be non-exposed with respect to that hyperplane. I mean, when the hyperplane has unique solution, right? Because let's say the quantum boundary is like that, we don't know, right? So then if you take this hyperplane, you will get many quantum extremal distribution. But again, this distribution can be produced by convex mixture of this, and this 2 point is called exposed. So this kind of work also one can do. Anyway, so if any other question is there.
Okay, I guess there are no other questions. So thank you, Souradeep, for this series of talks. And we end our meeting here. We'll let you know about the next meeting. So next week, there will not be any meeting. Sure. Okay. See you.
Bye.